Most years, the inner solar system welcomes just a handful of comets, but in late 2025, 7 major objects are diving in at once, including the interstellar heavyweight 3I/Atlas, growing bigger by the day. Astronomers are mapping out this unprecedented swarm, one not seen since modern telescopes began, plotting their approaches as they race past Earth and the Sun in a tight 6-month window. Some predict that all this action could even spike solar storms, and one of these visitors might flare bright enough for us to see with our own eyes. But why are so many coming at once, and just how much danger or wonder could this cosmic traffic jam bring? Let's break down the rarest comet calendar of our era. 7 major comets crowding the inner solar system in a single season is almost unheard of. Most years, astronomers might spot 1 or 2 bright comets passing close enough to study in detail, sometimes 3 if the surveys are lucky. But a year with 7, all diving in within just a few months, is the kind of event that stands out even in a century's worth of observing logs. Since the start of systematic sky surveys, think Pan-STARRS, Linear, and the Atlas project itself, no season has matched this kind of traffic. The last time comet counts even approached these numbers, telescopes were still recording on glass plates, and most discoveries happened by accident or word of mouth. Now, it's not just the total number that's remarkable. This swarm is different because it isn't a slow trickle over years. It's a concentrated rush, with each object threading through the inner solar system in rapid succession. Some are inbound from the farthest reaches, others are periodic returners, and one, 3I/Atlas, isn't even from our solar system at all. That interstellar wildcard alone would be newsworthy in any year. But paired with 6 other sizable comets, the odds become almost vanishingly small. Statistically, the average year since 2000 has seen just 1 comet reach naked eye brightness, with 2 or 3 others visible only through binoculars or telescopes. Many years go by with nothing but faint, distant fuzzballs. Even in so-called comet showers, brief periods when several objects happen to arrive together, numbers like 7 are virtually absent from the modern record. According to the Minor Planet Center's public logs, no season since the digital era began has hosted more than 4 major comets with perihelion inside 2 astronomical units, and that's not even considering the ecliptic alignment this group is showing. For context, comet discoveries have soared in recent decades as robotic surveys have swept the skies, but the vast majority turn out to be dim, distant, or short-lived. Bright, accessible comets remain a rare breed. The 2025 influx is so unusual that some astronomers have described it as a statistical outlier, the kind of event that might only happen once in many generations. That's why this isn't just a list of objects, it's a phenomenon in its own right, a true swarm that challenges what we expect from the solar system's usual rhythm. With so many icy visitors arriving nearly together, astronomers are treating this as a single, multi-act event. The focus has shifted from asking about individual comets to tracking their collective choreography, how their orbits, alignments, and solar encounters might interact or overlap. It's this rare convergence that's fueling both scientific excitement and public anticipation. Before digging into the details of what perihelion, superior conjunction, and ecliptic alignment really mean, it's worth pausing on just how rare it is to see 7 major comets sharing the stage at once. C/2022 N2 Pan-STARRS marks the opening of the 2025 comet season, reaching perihelion on July 31st at 3.82 astronomical units from the Sun. Its distant path keeps it well beyond Mars, where sunlight is thin and only the most sensitive telescopes can track its progress. Pan-STARRS sets the outer boundary for the swarm, a quiet start before the more dramatic arrivals. C/2025 R2 Swan follows, discovered on September 11th and racing to perihelion. Just a day later, September 12th, at 0.50 astronomical units. The highlight comes October 21st, when Swan will sweep past Earth at just 0.25 astronomical units, about 37 million kilometers. This close approach makes it a prime candidate for observation, especially in the pre-dawn sky of the northern hemisphere. Swan's rapid movement and geometry offer a rare chance to study a comet's interaction with both the Sun and Earth in real time. 414P/stereo will swing around the Sun on September the 27th, with a perihelion distance of 0.52 astronomical units. Its orbit dips below the ecliptic plane, making it a challenge for ground-based telescopes, often lost in solar glare. The stereo mission's namesake comet is better suited for spacecraft imaging, its low trajectory offering a different vantage point for solar studies. C/2025 K1 Atlas arrives next, reaching perihelion on October 8th at just 0.33 astronomical units, closer to the Sun than Mercury ever ventures. This tight solar pass means Atlas will undergo rapid changes, making it a key subject for monitoring outbursts and tail development. Its proximity to the Sun places it at the heart of the swarm's activity. 3I/Atlas, the interstellar visitor, will reach superior conjunction on October 21st, passing behind the Sun from Earth's perspective. Perihelion follows on October 29th at 1.36 astronomical units, just within Mars's orbit. With an inclination of about 5 degrees, 3I/Atlas tracks close to the ecliptic, sharing the sky with planets and other comets. For several days, both 3I/Atlas and SWAN occupy critical positions for solar interaction research, though neither is easily visible. C/2025 A6 Lemon peaks at perihelion on November 8th at 0.53 astronomical units. Its path keeps it visible in the evening sky after sunset, offering one of the most accessible observing windows of the group. Forecasts suggest it could reach magnitude 4 or even 3.5, potentially visible to the naked eye for northern observers in early November. 240P/NEAT completes the sequence, will reach perihelion on December 19th at 2.12 astronomical units. As a periodic comet, it's fainter and farther out, but its presence highlights the crowded state of the inner solar system by year's end. Each comet's path, perihelion date, and relationship to the ecliptic create a tightly packed calendar, setting the stage for the solar interactions that follow. Comet tails are more than just cosmic streamers. They're living records of the invisible forces at work in the solar system. When a comet approaches the Sun, solar radiation heats its nucleus, releasing gas and dust that form two distinct tails: a broad, pale dust tail and a narrow, electric blue ion tail. The ion tail, in particular, is a direct line to the Sun's magnetic field. It's made of charged particles, swept away by the solar wind, an unceasing flow of plasma and magnetic fields that spirals outward from the Sun at hundreds of kilometers per second. But the ion tail isn't permanent. It can be snapped off in an instant, a phenomenon known as a tail disconnection event. The physics behind this is rooted in magnetic reconnection. As a comet moves through the solar wind, it sometimes encounters abrupt changes in the interplanetary magnetic field, like a coronal mass ejection or a crossing of the heliospheric current sheet. These are not gentle transitions. The magnetic field can rotate by 90 degrees or more in minutes, and when that happens, the comet's plasma environment can't keep up. The old tail is cut loose, drifting off into space, while a new tail begins to grow, perfectly aligned with the new direction of the solar wind. One of the most dramatic examples was captured in April 2007 when the Stereo spacecraft watched a CME slam into Comet Encke. The ion tail was severed cleanly, with a visible gap forming near the nucleus and the old tail floating away. A textbook case that matched magnetohydrodynamic simulations almost frame by frame. These events aren't rare during solar maximum. With several comets diving near the ecliptic in late 2025, the odds of catching a live disconnection are higher than ever. The dust tail, by contrast, is less affected by these magnetic storms. It's governed by sunlight and gravity, not magnetism. Only the most powerful CMEs can reshape or truncate a dust tail, usually by stripping away part of the coma or redirecting the outflow. For most observers, the ion tail's sudden breaks and regrowth are the signature to watch, a direct sign of the Sun's restless energy at play written across millions of kilometers of space. Solar physicists are watching this comet swarm with a mix of anticipation and unease, and not just for the spectacle. Behind the scenes, a sharp debate is playing out over what these close passes might mean for the Sun's behavior. Some research groups, especially the NASA CCMC modeling team, argue that the sudden spike in cometary plasma and dust, especially from ecliptic-aligned comets, could actually nudge the Sun toward more frequent or intense outbursts. Their simulations show that when a dense, active comet crosses the heliospheric current sheet or passes through a coronal mass ejection, the magnetic geometry can shift rapidly, sometimes triggering a classic tail disconnection event. In these models, the Sun's magnetic field lines drape around the comet, and if a CME sweeps through at the right angle, the ion tail snaps off, sometimes within minutes. The CCMC's MHD runs suggest that with several comets in play, especially during solar maximum, the odds of witnessing multiple dramatic tail severings go up, and that the excess plasma might even help seed new instabilities in the solar wind. But not everyone is convinced. The Solar Orbiter and Parker Solar Probe teams point to their own in situ data, arguing that most tail disruptions are far subtler than the models predict. They've catalogued plenty of minor kinks and bends in comet tails that never turn into full-scale disconnections, even during strong CME events. Their field measurements show that small-scale turbulence, micro-reconnection, and the background variability of the solar wind can all play a role, sometimes more so than the big, headline-grabbing CMEs. In their view, the Sun's own magnetic cycles and large-scale field reversals are the real drivers, with comets acting more as passive tracers than active agents. They caution against overestimating the risk to satellites or power grids, noting that even during the 2007 Enki event, the operational impact was negligible. Still, with CME rates expected to hit 2 to 5 per week during the late 2025 solar maximum, both camps agree on one thing. This is a rare chance to test their theories in real time. Space weather officials are ramping up monitoring, and citizen scientists are prepping for a global campaign. If a major tail disconnection happens while a comet is in view, observers from backyard telescopes to spacecraft will be ready to catch it. For now, the debate has sharpened everyone's focus. Every new CME, every odd twist in a tail, could tip the scales in this ongoing scientific standoff. When astronomers first plotted the orbit of 3I/Atlas, the numbers did not fit any pattern known from homegrown comets. Its trajectory is hyperbolic, with an eccentricity well above 1, meaning it is not just visiting, it is passing through, never to return. That alone sets it apart. Only two other objects, Oumuamua in 2017 and Borisov in 2019, have ever been confirmed as interstellar before it. But Atlas is different in more ways than one. Early measurements from the Hubble and James Webb telescopes suggest a nucleus somewhere between 320 meters and 5.6 kilometers across. But the coma, the halo of gas and dust it is shedding as it nears the Sun, has already grown to about 700,000 kilometers wide. That is nearly the size of Jupiter, and it is expanding by the week. Unlike most comets, which spend eons locked in the outer reaches of our solar system before making a single pass near the Sun, Atlas comes from much farther away, likely ejected from another star system, carrying material forged in a different cosmic neighborhood. Its composition stands out too. Spectra reveal a coma dominated by carbon dioxide and other volatile gases, with water vapor scarce and cyanide detectable only in faint traces. These are chemical fingerprints rarely seen in such abundance on local comets. The object's motion is just as telling. It entered the solar system at a steep angle, skimming the ecliptic by only about 5 degrees, with a velocity that leaves no doubt about its foreign origin. The scientific payoff is enormous. Each observation is a chance to compare the building blocks of distant planetary systems with our own, and there is more at stake than just chemistry. As Atlas rounds the Sun, it leaves behind a trail of dust and debris that Earth may cross in 2026, a rare opportunity for planetary defense teams to monitor interstellar material up close. The story of 3I/Atlas is still unfolding, but even now, it is rewriting what we know about the boundaries of our solar system. From late October through early November 2025, the sky opens a rare window for comet watchers. No advanced equipment required, just a clear view and a bit of timing. The show will start before dawn on October 21st, when C/2025 R2 Swan comes closest to Earth, sweeping by at about 0.25 astronomical units. Even through a modest pair of binoculars, Swan's tail will stretch out to an astonishing 2.5 degrees, 5 times the apparent width of the full moon. Its head glows at magnitude 6 to 7, faint but within reach for anyone willing to rise early and scan the southeast sky. For most northern latitudes, Swan climbs to nearly 40 degrees above the horizon at civil twilight, making it a perfect pre-dawn target. Meanwhile, 3I/Atlas will slip behind the Sun at superior conjunction. While ground-based telescopes lose sight, the action shifts online. Solar observatories like SOHO's LASCO C3 coronagraph keep watch, capturing both 3I/Atlas and, at times, Swan as faint, moving points against the Sun's outer atmosphere. These real-time feeds are open to the public. Anyone can join the hunt for sudden changes, outbursts, or even a tail disconnection event triggered by a solar storm. By early November, C/2025 A6 Lemon will steal the spotlight in the evening sky. Forecasts place its brightness at magnitude 4, possibly even 3.5, enough to spot with the naked eye from dark sites, especially for viewers in the northern hemisphere. Lemon sits low in the southwest after sunset, its coma and tail brightening each night as it nears perihelion on November 8th. For many, this will be the easiest comet to see in years. Whether you're using binoculars, a backyard telescope, or simply your own eyes, this is a season to step outside and witness the solar system in motion. The best observing nights are October 21st for Swan's close pass and November 6th through 12th for Lemon's prime. For the comets hiding near the Sun, the world's coronagraphs are your window, just a browser click away. Forecasting comets is a lesson in humility, no matter how much data pours in. Every year, brightness predictions swing by as much as 2 magnitudes, sometimes more. A comet expected to blaze at magnitude 3 can fizzle to 5 or 6, while a faint, overlooked newcomer can suddenly erupt, outshining all expectations. These surprises come down to factors no model can fully pin down: grain size in the dust, the mix of ices, how sunlight penetrates a crust that might be meters thick. Even with the best thermophysical models, a slight shift in solar heating or a hidden fracture can change the story overnight. For 3I/Atlas, the uncertainties run even deeper. Its nucleus could be as small as 320 meters or as large as 5 kilometers. Current Hubble and JWST constraints bracket the range, but the true size remains elusive. The coma's dominance by carbon dioxide is clear from spectra, yet the full inventory of volatiles and dust is still out of reach. Without a strong detection of water or other familiar gases, every new dataset reshapes the working theories. The only certainty is that forecasts will evolve right up to and beyond perihelion. Looking ahead, the next generation of surveys, especially the Vera Rubin Observatory's LSST, promise to catch more of these wildcards. Routine, all-sky imaging will spot faint, fast-moving objects that today might slip through. But even in the LSST era, the science will be shaped as much by what we don't see coming as by what the models predict. For now, the best advice is to watch the sky with an open mind and expect the unexpected. 3. I/Atlas, with its vast carbon dioxide coma measured at over 700,000 kilometers wide, stands out for its interstellar origin and unknown composition. As researchers continue to monitor these objects, the 2025 swarm will test and expand our understanding of comet behavior and solar interactions, adding a new chapter to the ongoing story of our solar system.